everyone, and welcome back for another deep dive. We love to unpack some really interesting stuff, and today we're going to be looking at weather theory.
Yeah.
Specifically for pilots. So we're going to be taking apart Chapter 12 of a pilot training manual called Weather Theory, and I've got a great expert with me today to really pull out those key nuggets, those little golden pieces of information.
Absolutely.
That are going to be so helpful for us, whether you're just starting out on your aviation journey or you've been flying for a while. We're really going to focus on laying that solid foundation. So
Yeah.
I'm really excited to dive into this. So, okay, we all know weather's a big deal for pilots, but have you ever thought about what actually creates all that drama up there in the air?
Well, it's interesting to think that only a tiny fraction of the atmosphere is actually responsible for the vast majority of the weather that we experience.
Oh, really?
And when we're talking about this, we're talking about water vapor, which is, it's only about 1% of the atmosphere.
Wait, only 1%? That's wild. So how does something so small have such a huge impact on flight conditions?
Well, water vapor, it's very powerful. It plays a crucial role in cloud formation precipitation and even affects aircraft performance. And so it's something that pilots really need to understand how it interacts with, all the other elements of the atmosphere.
That makes sense. Now, I often hear about different layers of the atmosphere, and it's always kind of sounded to me like a giant layer cake.
Oh, yeah.
Each with its unique characteristics.
I like that analogy. That's good.
Right. So can we break down this layer cake?
Yeah. So just like a cake, there's one layer we're particularly interested in as pilots, and that's the troposphere, because that's where almost all of the weather happens.
Okay, so that's where the weather party is happening.
It is. It's where it's at.
And we're the guests trying to navigate through all the fun and excitement.
That's right. And as we climb higher in the troposphere, the temperature and pressure decrease. And so that decrease in pressure also means the air becomes less dense. And this is a concept referred to in our training manual as density altitude.
Right, density altitude. That's a big one that we hear all the time in our pilot training.
Yeah.
Why is it such a big deal for us when we're up in the air?
Well, density altitude affects almost every aspect of aircraft performance. So things like takeoff distance, rate of climb, even how our engines operate, are all affected by density altitude. And, the higher the density altitude, the thinner the air, the harder our aircraft has to work to perform.
Okay, so we're talking about this massive atmospheric ocean above us, but what actually gets all that air moving around in the first place?
Well, the primary driver is the uneven heating of the Earth by the sun. So the equatorial regions receive much more direct sunlight,
Right.
leading to warmer temperatures and less dense air, which rises, and then that creates an area of lower pressure.
So that warmer air rises, and then that cooler, denser air rushes in to replace it from the poles. Exactly. It sets up this continuous circulation pattern. But there's another force at play here that's essential for understanding these global wind patterns, and that's called the Coriolis force.
Oh, yes, the Coriolis force. I remember that from my training. But could you maybe break that down in a way that makes sense for those of us who aren't physics whizzes?
Yeah. So imagine you're drawing a straight line on a spinning globe. That line appears to curve, right? Well, that's essentially the Coriolis effect in action because the Earth is rotating. Anything traveling long distances like an air mass is going to get deflected. And in the northern hemisphere, that deflection is to the right. So our straightforward north-south circulation gets twisted, creating these familiar wind patterns like the trade winds.
So it's like those trade winds are constantly being nudged off course by the Earth's rotation.
They are. It's pretty amazing.
That's amazing.
Yeah.
Now, our source material mentions a really interesting fact about atmospheric pressure. It says that if you could weigh a column of air reaching to the top of the atmosphere, it would be about 14.7 pounds. That's right. And that's the weight of the atmosphere pressing down on us at sea level. But as we go up, as we ascend, that pressure decreases, which is why, we need pressurized cabins in aircraft when we go to higher altitudes.
Right. And we use instruments to measure all this pressure, right?
Absolutely. And the aneroid barometer is, basically what our altimeter is based on, helps us to determine our altitude based on those pressure changes.
Speaking of altimeters, the source also mentions the ISA, the International Standard Atmosphere.
Right.
What's the significance of that for pilots?
Well, the ISA is a really crucial reference point for aviation because it provides that standard for atmospheric pressure and temperature, and that ensures that all of our instruments are calibrated correctly and we have a common understanding of altitude.
Okay, now let's talk about wind. So let's say I'm planning a cross-country flight. How can understanding these high and low pressure systems, help me to make smarter decisions about wind direction and maybe even, save some fuel along the way?
Well, remember those circulation patterns we were talking about. So winds tend to flow parallel to isobars, those lines of equal pressure that you see on a weather map.
Yeah.
And the closer those isobars are together, the stronger the wind will be.
Right, and if they're spaced far apart, the winds are generally weaker?
Exactly.
Yeah.
So by analyzing those pressure patterns, you can get a good idea of where to expect tailwinds or headwinds along your route if you're flying from west to east, for example. Favorable winds would generally be found along the northern side of a high-pressure system or the southern side of a low-pressure system.
So it's like we can use those pressure systems to our advantage and kind of ride those tailwinds and avoid those headwinds as much as possible.
Absolutely. It's like getting a free boost from Mother Nature.
I love it. Now, have you ever been flying and felt those sudden jolts, especially on a hot day?
Yeah.
Those can be a little unnerving.
They can, and that's likely convective currents at work.
Yeah.
These currents occur when different surfaces heat up unevenly. Think about a paved runway versus a nearby lake on a sunny day.
Oh, yeah.
The air over the pavement is going to get much hotter and rise, and so that creates those updrafts that we feel as turbulence.
So as pilots, we need to be particularly aware of these convective currents during takeoff and landing, right? Because those sudden updrafts and downdrafts can really throw us off.
Absolutely. Those updrafts can create what we call a ballooning effect, which could cause us to overshoot the runway during landing.
Yeah.
And then downdrafts over, cooler surfaces can have the opposite effect, causing us to land short.
Okay, so understanding these local wind patterns, especially around airports, is so crucial for safe flight operations.
It is.
Now let's talk about atmospheric stability for a moment.
Okay.
And this concept always reminds me of kind of the mood swings of the sky.
I like that analogy.
So
think of a stable atmosphere as a very calm and predictable friend.
okay.
Small disturbances tend to just kind of disappear quickly, whereas an unstable atmosphere is like that friend who's prone to sudden outbursts.
Yeah.
So in an unstable atmosphere, those small disturbances can grow really rapidly, leading to turbulent air, massive cloud formations, even severe weather.
Wow. Now our source material mentions adiabatic lapse rates, which sounds a little intimidating.
Yeah.
What exactly are those, and how do they relate to this concept of atmospheric stability?
Well, adiabatic lapse rates describe how temperature changes with altitude.
Okay.
So as air rises, it expands and cools. The lapse rate tells us how much the temperature changes for every 1,000 feet of altitude change.
So if the air is rising and cooling quickly, that's a sign of an unstable atmosphere.
You got it. And that rapid cooling can lead to condensation and cloud formation. The source material states that unsaturated air cools at a rate of about 5.4 degrees Fahrenheit for every 1,000 feet of altitude gain. And when that air rises and cools enough to reach its saturation point, that's when those clouds form.
Oh, so that's how those beautiful cumulus clouds we see, on a warm day are formed.
Exactly.
It's reaching that dew point
Right.
as it rises and cools.
That's right.
Now, the source also mentions temperature inversions.
Yeah.
What are those, and why should pilots care?
Well, a temperature inversion is a situation where the temperature of the air increases with altitude.
Oh, wow. So it's like the opposite of what we normally expect?
Exactly.
Instead of getting colder as we go up, it gets warmer?
Yeah, and these inversions create very stable air near the ground, and that can actually trap pollutants and reduce visibility.
Oh, wow.
Sometimes significantly.
So they can be associated with, like, fog and haze?
They can, and pilots need to be particularly aware of inversions because they can make takeoffs and landings very challenging, especially if the visibility is reduced.
So knowing how to identify and anticipate these inversions is crucial for us.
It is.
Now let's talk about moisture, which is another key element in this whole weather game. And I'm always hearing about dew point, but what does that actually tell us? And how can we use that information in our pre-flight planning?
Well, the dew point is the temperature at which the air can hold no more moisture. So when the air temperature cools to the dew point, that invisible water vapor in the air begins to condense into visible forms like fog or dew.
Ah, so that's why we see dew on the grass in the morning.
Exactly.
Because the air temperature has cooled down to the dew point overnight, and that excess moisture has condensed.
That's right.
So pilots use this dew point information to predict cloud formation and potential weather hazards.
Absolutely. So knowing the dew point helps us understand how close the air is to saturation.
Okay.
And if the temperature and dew point are really close together, it's a good indication that clouds or fog might form.
Okay.
And that could impact visibility.
So the closer the temperature is to the dew point, the higher the chance of fog or cloud formation.
Exactly.
Our source even gives a handy calculation for estimating that cloud base height based on the temperature and dew point.
It does. And that's a really valuable tool for pilots, especially when flying under visual flight rules. Because knowing the cloud base helps us to determine if we can maintain visual separation from the clouds, or if we might need to rely on our instruments.
That's really practical information.
Yeah.
Okay, so let's say I'm planning a flight and I see that the temperature and dew point are very close together.
Right.
What kind of things should I be thinking about in terms of potential hazards?
Well, you should anticipate the possibility of fog or low clouds and reduced visibility. You might need to delay your flight or choose a different route that avoids those areas, or be prepared to fly using instruments if necessary.
Okay, now our source mentions that moisture in the atmosphere exists in 3 states.
Yes.
Liquid, solid, and gaseous.
Right.
And it can transition between these states
Yeah.
through processes like evaporation, condensation, sublimation, and deposition.
Exactly. And remember, water vapor is primarily added to the atmosphere through evaporation and sublimation.
Okay, so those are the 2 main ways that it gets added to the air. Now, what about relative humidity?
Yeah.
It's a term we hear all the time, but how does it relate to our understanding of weather,
Yeah.
especially as pilots?
Well, relative humidity is basically a percentage that tells us how much moisture is currently in the air compared to the maximum amount it could hold at that temperature.
Oh, so 100%. Relative humidity means the air is completely saturated, like a sponge that can't absorb any more water.
Exactly. And at that point, any further cooling is going to cause condensation,
Okay.
leading to the formation of fog clouds, dew, or precipitation.
Our source actually uses a really helpful example of a cubic meter of air
Yes.
to illustrate this relationship between relative humidity temperature and dew point.
Right.
And it shows how the amount of water vapor the air can hold changes as the temperature changes.
Yeah, it's a great visualization to
Yeah.
help us understand those concepts.
So the warmer the air, the more moisture it can hold before reaching that saturation point.
Exactly.
And as the air cools, its
Mhm.
ability to hold moisture decreases, which is why we often see, condensation and cloud formation in the evenings as the temperature drops.
That's right.
Okay, so if we're flying in an area with high relative humidity and we encounter cooling temperatures, we should be prepared for the possibility of cloud formation or even precipitation.
Absolutely. Knowing that relative humidity helps us to anticipate those changes and make more informed decisions about, our flight path and altitude.
This has been so insightful. I mean, it's amazing how these seemingly simple concepts like dew point and relative humidity play such a crucial role in understanding weather patterns and, for us making informed decisions as pilots.
I agree, and we've only just scratched the surface.
I know there's so much more to explore in this fascinating world of weather and how it impacts aviation. So let's take a quick break and we'll be right back to dive even deeper. Okay, so we've talked about moisture, but now let's zoom out and look at the bigger picture. Literally, I'm talking about air masses. I always picture them as these giant bubbles of air, each with its own unique personality based on where it came from.
That's a great way to think about it. Each air mass carries those characteristics of its source region, whether it's a frigid polar region, a warm tropical ocean, or a dry desert.
Right. So it's like each air mass has its own travel history and it's picked up, souvenirs along the way. And we categorize these air masses based on their temperature and moisture content.
That's right.
Right.
We have polar and tropical air masses based on temperature,
Okay.
and then maritime and continental air masses based on moisture.
So like a continental polar air mass would be forming over those cold, dry land areas,
Yes.
and bringing us that crisp, cool air that we often feel in the winter.
Exactly. And then on the other hand, you have a maritime tropical air mass originating over those warm, humid ocean regions,
Right.
bringing us those muggy summer days.
It's amazing how those different air masses create such distinct weather patterns. Now, our source explains that as these air masses move and they encounter different surfaces, they start to modify.
Yes,
So their temperature and moisture content kind of adjusts to that new environment.
that's right. So think about this. An air mass moving over a warmer surface is going to become unstable,
Okay.
often leading to the formation of, those puffy cumulus clouds we see on warm days,
Right.
and sometimes even, showers or turbulence.
So it's like the air mass is getting energized by that warmer surface.
Okay.
And what happens when it encounters a colder surface?
When an air mass moves over a colder surface, it becomes more stable, and this increased stability can actually trap pollutants near the ground, leading to reduced visibility,
Okay.
and in some cases even fog.
So understanding how those air masses interact with different surfaces can really help us anticipate, those potential weather changes as those air masses move across different regions.
It does. It's like having a sneak peek into what the air mass has learned on its journey
Right.
and how it might behave as it encounters these new environments.
Okay, so now let's talk about what happens when these massive air masses collide.
Yeah,
I always picture it as like a clash of the titans.
that's a good way to put it. You're talking about fronts those boundaries between two air masses with different characteristics.
Okay.
They're the driving force behind a lot of the weather changes that we experience.
And our training manual highlights 4 main types of fronts.
Yes,
Warm fronts, cold fronts, stationary fronts, and occluded fronts.
that's right. And each one brings its own set of weather patterns and potential hazards. Understanding how these fronts behave is key for pilots, especially when planning and executing our flights.
Absolutely. So let's start with warm fronts. I remember from my training that they're generally slower moving than cold fronts.
Yes.
How would you describe a warm front to someone who's maybe just starting out on their aviation journey?
Well, imagine a warm front as a gentle ramp of warm air pushing over a mass of colder air. This gradual slope means we'll see a gradual change in weather as that warm front approaches.
Okay, so if I'm flying towards a warm front, what kind of visual cues should I be looking for?
Well, first, you'll likely see those high, wispy cirrus clouds. Often they look like feathery streaks across the sky. And then, as the front gets closer, you'll start to see lower, thicker clouds, like altostratus and nimbostratus.
Okay, and what about precipitation? What can we expect ahead of a warm front?
Well, as that warm, moist air rises and cools, we often see precipitation ahead of the warm front. And it can be in the form of light rain, drizzle, or snow, depending on the temperature.
Now, our source material also points out that sometimes those big, powerful cumulonimbus clouds, the thunderstorm clouds,
Yes.
can develop ahead of a warm front, especially during those summer months.
That's right. And those embedded thunderstorms can be really tricky because they can be hidden within those larger cloud systems,
Right.
making them harder to see and potentially more dangerous.
Okay, so we need to be extra vigilant when we're flying near warm fronts, especially in those summer months when those thunderstorms are more likely to pop up.
Right.
Okay, so let's shift gears to cold fronts. Now, these are like the assertive siblings of warm fronts, right?
Yeah, exactly. Cold fronts are fast-moving boundaries where a cold air mass is pushing its way and forcing that warmer air upward.
So instead of that gentle ramp, we've got more of a steep wall of cold air pushing against that warmer air.
Yes, and that rapid lifting of that warm air is what triggers those more dramatic weather changes that we often see with cold fronts.
Like those, heavy downpours, gusty winds, sometimes even hail or tornadoes.
Exactly. You'll often see towering cumulus clouds, heavy rain, and thunderstorms along and ahead of that cold front.
Our source material gives a really vivid example of a flight heading towards an approaching cold front. And as that flight gets closer, the weather deteriorates really rapidly, going from clear skies to overcast conditions with thunderstorms and heavy rain.
It's a good reminder that cold fronts can bring those sudden and significant weather changes
Right.
that could be challenging and potentially hazardous for pilots.
Now, our source also mentions those lines of thunderstorms, called squall lines, as a potential hazard associated with cold fronts.
Right. Squall lines can form ahead of that fast-moving cold front, creating this line of intense thunderstorms that can stretch for hundreds of miles.
Wow.
They can be incredibly powerful and dangerous to encounter in flight.
So being able to recognize those signs of an approaching cold front and understanding those potential hazards is absolutely crucial
It is
for
essential.
maintaining safe flight operations.
Okay.
So we've talked about warm fronts, cold fronts. Let's compare them for a moment.
Yeah.
Our source material gives us a helpful summary of their key differences.
It does. As you mentioned, cold fronts move much faster than warm fronts.
Right.
They also have a steeper slope, meaning that air is forced upward more rapidly, leading to those more intense weather events.
Right. And cold fronts generally bring that narrow band of heavy precipitation right along the front, whereas warm fronts tend to produce a wider area of lighter precipitation ahead of the front.
Exactly. And another key difference is that cold fronts tend to clear out pretty quickly, leaving behind cooler, drier air. Warm fronts, on the other hand, can kind of linger, bringing those overcast skies and low ceilings that can persist for days.
So knowing which type of front we're dealing with can really help us anticipate
It can.
the duration and intensity of those weather changes.
Absolutely. It's all about understanding those patterns and being prepared for the potential challenges.
Okay, so we've covered the movers and shakers, the warm fronts, the cold fronts.
Right.
But what about those times when those air masses just decide to hang out and stare each other down?
You're talking about stationary fronts.
Yes.
It's that stalemate between the cold air mass and a warm air mass where neither one has enough force to push the other one out of the way.
And the weather associated with a stationary front can be kind of a mixed bag, right?
It can be.
It's like they can't decide whether to be a warm front or a cold front.
Right. We might see a combination of warm front and cold front weather. So things like clouds, precipitation, even thunderstorms.
And these stationary fronts can just hang around for days,
It can.
leading to these prolonged periods of unsettled weather. which can make flight planning really tricky.
Yeah.
And then finally, we have those occluded fronts,
Right.
which are kind of like the grand finale of frontal systems.
That's right.
It's where a fast-moving cold front overtakes a slower-moving warm front and essentially lifts that warm air mass off the ground.
Precisely. And depending on the temperature differences between those colliding air masses, we can get either a cold front occlusion or a warm front occlusion.
And our source material explains these occluded fronts in detail. It seems like they can bring a mix of weather.
They can.
Including clouds, precipitation, and even thunderstorms.
Yeah, and those embedded thunderstorms within an occluded front can be particularly dangerous.
Oh, wow.
Because they can be really difficult to detect visually.
Especially if they're hidden in those larger cloud systems.
Exactly.
So it's essential to have a good understanding of how to interpret those weather charts.
Yes.
And radar imagery to identify those potential hazards.
Absolutely.
Now let's circle back to wind shifts for a moment.
Yeah.
Our source material emphasizes that fronts are the boundaries between areas of high and low pressure, which means we often see those wind shifts as those fronts pass through.
That's right, and those wind shifts can be sudden and significant, especially with cold fronts.
Okay, so if I'm approaching a cold front, what kind of wind shift should I be prepared for?
As a cold front passes, the wind will typically shift from a southerly or southwesterly direction to a northwesterly or northerly direction.
And these shifts can happen really quickly.
They can, especially with those fast-moving cold fronts, and those sudden shifts can dramatically affect our airspeed and our controllability, particularly close to the ground during takeoff or landing.
That's why staying aware of those approaching fronts and anticipating those wind shifts is so crucial for maintaining safe flight operations.
It is.
Now let's shift gears again and talk about one of the most powerful and awe-inspiring weather phenomena we encounter as pilots. Thunderstorms.
Thunderstorms are certainly a force to be reckoned with.
They are.
They can produce those intense updrafts and downdrafts, heavy rain, hail, lightning, even tornadoes. As pilots, we need to treat them with the utmost respect.
Absolutely. Our source material actually breaks down the life cycle of a thunderstorm into 3 stages.
Does.
Cumulus, mature, and dissipating.
Right.
Can you kind of walk us through those stages?
Yeah.
And what we should be looking for as pilots?
Of course. So the cumulus stage is like the birth of a thunderstorm. It starts with warm, moist air rising and forming those billowing cumulus clouds. And as long as there's enough moisture and instability, that cloud continues to grow, vertically fueled by those strong updrafts.
So those cumulus clouds are like the building blocks of a thunderstorm.
Exactly. And if conditions are right, those cumulus clouds can grow into towering cumulus clouds.
Wow.
Reaching tens of thousands of feet high.
And then we move into the mature stage, which is when things really start to get intense.
Precisely in the mature stage, the updrafts are at their strongest. But now we also have downdrafts developing as precipitation starts to fall.
Oh, so it's like a tug of war between those rising and falling air currents.
That's a great analogy. And this stage is when we see the heaviest rain, hail, and the most intense lightning. The top of the cloud often spreads out into that classic anvil shape, which is a telltale sign of a mature thunderstorm.
Okay, so if we see that anvil-shaped cloud, we know we're dealing with a fully developed thunderstorm.
Right.
And we need to stay well clear.
Absolutely.
What happens in the dissipating stage?
Well, as the name suggests, the storm starts to weaken in this stage. The downdrafts spread out, cutting off the supply of warm, moist air that fuels the storm, and eventually that thunderstorm just fades away.
So it's like the storm is running out of steam.
Exactly. The rain lightens up, the lightning becomes less frequent, and eventually that cloud dissipates.
Now let's be realistic here. Trying to fly through a thunderstorm in a light aircraft is essentially a recipe for disaster.
I couldn't agree more. Those intense updrafts and downdrafts can easily exceed the capabilities of most small aircraft. The hail, the lightning, the severe turbulence can all cause catastrophic damage.
Our source material provides this really powerful illustration of the movement and turbulence associated with a maturing thunderstorm.
Yes.
And it really highlights how strong those updrafts and downdrafts can be and the hazards that they pose.
It's a sobering reminder that we need to treat thunderstorms with the utmost respect and always err on the side of caution.
Absolutely.
Avoiding them altogether is the safest course of action.
Our source emphasizes that all thunderstorms pose hazards to aviation, even those that might appear less intense from a distance.
That's an important point. While not every thunderstorm contains every hazard, it's impossible to tell from a distance which threats a particular storm might present.
Right.
They can be unpredictable and dangerous.
So let's delve into those specific hazards in a little more detail, starting with those lines of thunderstorms we talked about earlier, the squall lines.
Right. A squall line is a line of thunderstorms that can stretch for hundreds of miles.
Yeah.
These lines often form along or ahead of cold fronts
Right.
and can be extremely intense, packing, heavy rain, hail-strong winds, and even tornadoes.
Our source material describes squall lines as the single most intense weather hazard to aircraft.
Wow.
And I can certainly see why.
I agree. Encountering a squall line can be like flying into a wall of severe weather.
And then there are tornadoes, those terrifying, violently rotating columns of air that can cause incredible damage.
Tornadoes form when the powerful updrafts in a thunderstorm start to rotate, creating this vortex that can extend from the cloud base all the way to the ground, and the wind speeds in a tornado can reach hundreds of miles per hour, making them one of the most destructive forces of nature.
And the damage that they can inflict on an aircraft is unimaginable.
Yeah.
So it's crucial to stay well clear of any thunderstorms that have the potential to spawn tornadoes.
Absolutely. If you see a tornado or suspect one might be developing, avoid the area at all costs.
Our source material also highlights those dangers of turbulence
Right.
associated with thunderstorms.
Turbulence is a major hazard associated with thunderstorms. It can occur both inside and outside the thunderstorm cloud, and it's caused by the interaction of those powerful updrafts and downdrafts.
And turbulence can range from mild to severe, right?
It can. And encountering severe turbulence can be incredibly dangerous, especially for smaller aircraft. It can cause structural damage, loss of control, and even injuries to passengers and crew.
So we need to be very careful when we're flying in the vicinity of thunderstorms.
We do.
Now, what about icing? That's another serious threat that we face as pilots, especially when flying in those colder temperatures.
Icing is a significant hazard, particularly in the presence of thunderstorms. Supercooled water droplets in a thunderstorm can freeze on impact with an aircraft,
Right.
leading to rapid ice accumulation.
And it can happen really quickly.
Ice can accumulate on those critical surfaces like wings, propellers, and control surfaces in a matter of minutes, making it crucial to have effective de-icing and anti-icing equipment and to avoid those areas of known or forecasted icing conditions.
So knowing how to identify those conditions and having the proper equipment on board is essential.
It is.
And we can't forget about hail, those chunks of ice that can range in size from small pellets to baseballs.
Hail is another significant hazard it forms. When supercooled water droplets in a thunderstorm are tossed up and down by those powerful updrafts, collecting more and more ice until they become too heavy to stay aloft.
Our source material provides a really vivid description of the damage that hail can inflict.
It does.
Even hailstones larger than a half an inch in diameter can dent the aircraft's skin crack windshields and even damage engines.
It's a serious threat, and another reason why avoiding thunderstorms altogether is always the best strategy.
Now, what about lightning? I mean, it's a spectacular sight,
It is.
but it also poses a real danger to aircraft.
Lightning is a powerful electrical discharge that can strike an aircraft, directly damaging the structure and potentially affecting electrical systems.
And it can also cause temporary blindness for pilots, disrupt radio communications, and even induce errors in magnetic compasses.
That's right. While lightning strikes rarely cause major accidents, they can still be dangerous and disruptive.
So it's another reason to steer clear of those thunderstorm cells. Now let's talk about how thunderstorms affect ceiling and visibility, which are, critical factors for us when we're flying under VFR.
Thunderstorms often bring heavy rain, which can significantly reduce visibility, making it very difficult to maintain visual separation from other aircraft and obstacles. And the cloud base itself can create a very low ceiling, making VFR flight impossible.
And our source material points out that thunderstorms can cause these rapid pressure changes,
Yes.
which can affect our altimeters.
That's an important point. Those rapid pressure changes, especially when flying near a thunderstorm, can lead to significant altitude errors if we're not receiving updated altimeter settings,
Right.
potentially putting us at risk.
So we need to be very diligent about obtaining those updated altimeter settings, especially when flying in areas where thunderstorms are present or forecasted.
Absolutely, and it's a good practice to check those altimeter settings frequently when flying near thunderstorms or any areas of rapidly changing weather conditions.
Another hazard our source mentions is the potential for engine water ingestion,
Right.
especially in turbine engines. What's the concern there?
This is a concern when flying through areas of heavy rain associated with thunderstorms. Those updrafts can concentrate those raindrops, creating a situation where the engine might ingest more water than it's designed to handle.
And that can lead to engine flameout or even structural damage.
It can. It's another reason why avoiding thunderstorms altogether is the safest option.
Now, our source material also mentions a couple of other interesting thunderstorm phenomena.
Yes.
Air mass thunderstorms and steady-state thunderstorms.
Right.
What's the difference between these two types?
Air mass thunderstorms are those isolated storms that typically form due to surface heating. They tend to be less intense and shorter lived than steady-state thunderstorms.
So those are like the pop-up thunderstorms that we sometimes get on a hot summer afternoon.
That's exactly. They usually form in the late afternoon or early evening as the ground heats up and the air becomes unstable. Steady state. Thunderstorms, on the other hand, are associated with weather systems like fronts or areas of converging winds. These storms are often more organized and longer lasting, and they can be much more intense than air mass thunderstorms.
Our source mentions that steady-state thunderstorms can sometimes form into those squall lines
That's right.
that we talked about earlier.
They can also be embedded within those larger cloud systems, making them more difficult to detect visually.
So it's like they're hiding within those larger weather systems.
Exactly.
Which makes them even more treacherous.
It does. Being able to identify these different types of thunderstorms and understanding their characteristics can help us make better decisions about, flight planning and avoiding those potentially hazardous weather conditions.
Okay, now let's talk about a concept that always reminds me of those intricate weather maps with all those lines and symbols, air masses and fronts.
Air masses and fronts are essential components of weather systems, and understanding how they interact is crucial for pilots.
I always picture air masses as these giant bubbles of air,
Right.
each with its own distinct personality based on where it formed.
That's a great analogy. The source material explains that air masses get their characteristics from their source regions, whether it's a frigid polar region, a warm tropical ocean, or a dry desert.
Right, and we classify these air masses based on their temperature and moisture content. So we've got our polar and tropical air masses based on temperature, and our maritime and continental air masses based on moisture.
Precisely. For example, a continental polar air mass forming over those cold, dry land areas brings us that crisp, cool air we often experience in the winter.
Right. And on the flip side, maritime tropical air mass originating over those warm, humid ocean regions brings us those muggy summer days.
Exactly. And as these air masses move and encounter different surfaces like warmer land or cooler water, they start to modify their temperature and moisture content adjust to that new environment.
So it's like they're constantly evolving based on their journey.
They are.
Our source explains that an air mass moving over a warmer surface becomes unstable, often leading to those puffy cumulus clouds, showers, and even turbulence.
It does. And conversely, an air mass moving over a colder surface becomes more stable, which can trap those pollutants near the ground, leading to poor visibility and sometimes even fog. And let's talk about what happens when those massive air masses collide. We get fronts.
It's like a clash of the titans fronts, are those boundaries between two air masses with different characteristics, and they're the driving force behind many of the weather changes we experience.
Our source material describes four main types of fronts: warm fronts, cold fronts, stationary fronts, and occluded fronts.
Right, and understanding how these fronts behave is crucial for pilots because they can bring those significant shifts in wind temperature and precipitation.
Let's start with warm fronts. Our source material describes them as those slow-moving boundaries where a warmer air mass is advancing and replacing a colder air mass. Exactly, and because that warm air is less dense, it rides up and over the colder air, creating a gradual slope.
Okay, so the approach of a warm front is usually marked by those high, wispy cirrus clouds first.
Yes.
And then followed by lower, thicker clouds like altostratus and nimbostratus as the front gets closer.
That's a good observation. And as that warm, moist air rises and cools, we often see precipitation ahead of the warm front, typically in the form of light rain drizzle or snow, depending on the temperature.
Our source material also highlights that cumulonimbus clouds, those thunderstorm clouds, can develop ahead of a warm front, especially during those summer months.
It's true. And those thunderstorms can be embedded within those larger cloud systems, making them harder to see and potentially more dangerous.
No, cold fronts are a different beast altogether. They're those fast-moving boundaries where a cold air mass is bulldozing its way and pushing that warmer air up and out of the way.
Exactly. And because that cold air is denser, it wedges itself under the warmer air, forcing it to rise rapidly.
And that rapid lifting is what triggers those often dramatic weather changes associated with cold fronts, right?
It is. We often see towering cumulus clouds, heavy rain, thunderstorms, and even hail or tornadoes along and ahead of a cold front.
The source material gives a great example of a flight heading towards an approaching cold front. As the flight gets closer to the front, the weather deteriorates rapidly, going from VFR conditions to overcast skies, thunderstorms, and heavy rain.
It's a stark reminder that cold fronts can bring those significant and rapid weather changes that can pose serious challenges for pilots.
Our source also mentions squall lines, which we talked about earlier, as a potential hazard associated with cold fronts.
Right, squall lines can form ahead of a fast-moving cold front and bring those intense, organized lines of thunderstorms that can stretch for hundreds of miles.
Now let's compare those warm and cold fronts for a moment. The source material provides a helpful summary of their key differences.
It does, as you mentioned. Cold fronts move faster than warm fronts. They also have a steeper slope, meaning the air is forced upward more rapidly, leading to those more intense weather events.
Right, and cold fronts usually bring that narrow band of heavy precipitation right along the front, while warm fronts tend to produce a wider area of lighter precipitation ahead of the front.
Exactly. And another key difference is that cold fronts tend to clear out quickly, leaving behind cooler, drier air, while warm fronts can linger, bringing those overcast skies and low ceilings that can persist for days.
So how about those stationary fronts? What happens when those two air masses just refuse to budge?
It's a stalemate when a cold air mass and a warm air mass meet, but neither one has enough force to push the other out of the way. We get a stationary front.
And the weather associated with a stationary front can be a bit of a mixed bag, right?
It can be. We might see a combination of warm front and cold front weather, things like clouds, precipitation, and even thunderstorms.
And those stationary fronts can hang around for days, leading to prolonged periods of unsettled weather.
They can. And finally, we have those occluded fronts, which are like the grand finale of frontal systems.
They form when a fast-moving cold front overtakes a slower-moving warm front, essentially lifting that warm air mass off the ground.
Exactly. And depending on the temperature differences between those colliding air masses, we can get either a cold front occlusion or a warm front occlusion.
Our source material provides a detailed explanation of these occluded fronts, and it seems like they can bring a mix of weather, including clouds, precipitation, and even thunderstorms.
They can. And those embedded thunderstorms within an occluded front can be particularly dangerous because they can be difficult to detect visually.
Now let's circle back to wind shifts for a moment. Our source material emphasizes that fronts are the boundaries between areas of high pressure, which means we often see those wind shifts as those fronts pass through.
That's right. And those wind shifts can be sudden and significant, especially with cold fronts.
So it's crucial for pilots to be aware of these potential wind shifts, especially during takeoffs and landings.
Absolutely. A sudden shift from a tailwind to a headwind can dramatically affect our airspeed and controllability, particularly close to the ground.
Wow. We have really covered a lot of ground today, from those tiny water vapor molecules to those massive clashing air masses. It's amazing to think about, all the stuff going on up there in the atmosphere above us.
It really is.
So what are some key takeaways that you think our listeners should keep in mind, especially when they're getting ready for, their next flight?
I think the most important thing to remember is that, weather is a dynamic and complex system. It demands our respect as pilots in understanding the basics, that weather theory, knowing how to interpret those weather reports and recognizing potential hazards. These are all crucial for flying safely.
Yeah, I totally agree. And I think it's important to remember, too, that, weather isn't just some abstract concept that we study for a test. It has a real impact on our aircraft's performance and our ability to make those safe decisions up in the air.
It absolutely does. Weather influences everything from our takeoff and landing distances to rate of climb fuel consumption, even our ability to control the aircraft.
It's really a make or break factor.
It is.
In aviation, and our source material does a great job of emphasizing that weather knowledge isn't just theoretical, it's practical and essential.
It is.
For anyone who wants to fly safely.
It really encourages pilots to continue learning and expanding their weather knowledge throughout their flying careers. There's always something new to discover about the atmosphere and how it affects our flights.
Speaking of expanding our knowledge, our source material mentions several additional resources that pilots can explore to really dive deeper into, those specific weather topics. There are advisory circulars, the Pilot's Handbook of Aeronautical Knowledge, and the Aeronautical Information Manual. Have you found those helpful in your own pilot journey?
Absolutely. Those are all excellent resources.
Right.
And they provide, much more in-depth information on specific weather phenomena, things like microbursts or mountain waves. And they explain how those could affect aviation.
So it's like having a whole library of weather wisdom at our fingertips. Now, before we wrap up this deep dive, let me ask you this. Given all that we've learned today about weather theory, What are some key areas that you would recommend our listeners focus on when they're planning, their next flight?
That's a great question. I think it's crucial for pilots to develop a personalized pre-flight weather checklist. This checklist should be tailored to their specific route, the type of aircraft they're flying, their level of experience. Some important areas to include might be understanding the current and forecast weather patterns along their route, identifying potential hazards like thunderstorms or areas of low visibility, and knowing how to access and interpret the latest weather information from, those various sources.
Those are all such excellent points. So it's not just about knowing the theory, it's about applying that knowledge to our specific flight plans and being
Yeah.
prepared for those real-world weather scenarios.
Exactly. And remember, weather is always changing, so
Yeah.
staying informed and being adaptable is key to flying safely and confidently.
Well said. A huge thanks to you for sharing your insights with us today. I know I learned a ton, and I'm sure our listeners did too. And to our listeners out there, happy landings. We'll catch you on our next deep dive into the fascinating world of aviation.